Okay, so and solenoid, you know that what is the magnetic field due to a solenoid? Mu naught Ni. N is the number of turns per unit length, small n multiplied by the current. Okay, so this question is, we have a solenoid of length 0 point. So this question is, you have a solenoid and the length of the solenoid is 0.5 meters. Okay, so the length, or you can say L, is equal to 0.5 meters. This is the length of the solenoid, not the length of the wire. Solenoid has a radius of 1 centimeter. Usually the radius component is no more useful for us. Radius of 1 centimeter, I'm not touching it. Okay, and is made up of 500 turns. So turns will be capital N, children. Turns are 500. So by this you can take out turns per unit length. N is equal to capital N by L. So it should be 500 divided by 5 into 10 to the power minus 1. So how much is it? This is 5 into 10 to the power 2 divided by 5 into 10 to the power minus 1. So 2 minus 1. So it becomes 10 to the power 3 turns per meter. Is this understood? Okay. It carries a current of 5 ampere. So let's take the current. The current is 5 ampere. We need to find out what is the magnitude of the magnetic field inside the solenoid. What is the magnitude of the magnetic field inside the solenoid? Would you give a try to this one? Very easy. B is, what is the funda for B? Mu naught N into I. मोनी जैसा पढ़ सकते हैं आप इसको. And mu naught, you know, right? Mu naught by 4 pi is equal to 10 to the power minus 7. So mu naught can be written as 4 pi 10 to the power minus 7, 10 to the power 3, and the current is how much? 5. 4 pi 10 to the power minus 7, 10 to the power 3 into 5. So it's around 6.28. Pretty straightforward problem. If you have any confusion, always remember, if this is my solenoid, length of the solenoid is this one. This is called the length of the solenoid. Length of the wire is a different concept. Length of the wire is when the wire is stretched out. So in that case, the radius helps you. If you know what is pi d, circumference of each loop, and you multiply with the number of turns, you get the length of the solenoid, right? Or else suppose number of turns were not given to you and they had given you the radius of the solenoid and length of the wire, then you need number of turns. So how will you find out number of turns? The length divided by pi d, or pi 2 pi r. Circumference, each circle is one circumference. So the length divided by the circumference will give you number of circumferences, which is nothing but the number of turns. Do you agree? So radius is not the useless item. The radius finds its use if the number of turns is not given to you and the length of the wire is given to you. Clear on this one? Okay. Then last class we had studied about the what do you call the definition of ampere and what is the magnetic field that one wire puts on the other. So that was equal to mu naught Ia Ib, if you remember, right? So we had run mu naught Ia Ib by 2 pi d. D is the distance between the two wires. Okay? Based on that, we have a question. The question is a little bit longer. So let's see. The horizontal component of Earth's magnetic field at a certain place. So the Earth's magnetic field. So the magnetic field of Earth has got it's a vector, and its horizontal component is some blah blah, is from geographic south to geographic north. Okay, geographic south to geographic north. So let's just make a diagram, the magnetic field is from geographic south to geographic north. I think fair enough if I write like this. This is the horizontal component of the Earth's magnetic field at a particular point, and it points from geographic south to geographic north. So I'm saying that this is south and this is north. And let's see what it says. It has a value of 3 into 10 to the power minus 5 Tesla. 3 into 10 to the power minus 5 Tesla. Right, no confusion. A very long straight conductor. Now you have a very long straight conductor carrying a steady current of 1 ampere. Okay. Carrying a steady current of 1 ampere. What is the force per unit when it is placed on a horizontal table and the direction of the current is from east to west? That means the current's direction is from east to west. So your current is in this direction. Okay. The current is pointing from going from east to west. So definitely the angle between them will be how much? 90 degree, and the current that this one is carrying is around 1 ampere. I am supposed to find out what is the force per unit length on it. Force per unit length. So how do you define the force? Force is given by I L cross B. Do you agree or not? And you are asked to find out force per unit length. So basically they are asking you to find out F upon L. So F upon L will be I and L cross B. Here L cross B means how much beta? L cross B will be equal to sine of 90 degree, which is equal to 1, right? So I straight away multiplied by B, force per unit length. Clear? I into B. So answer is simply, so the answer comes 3 into 10 to the power. How much is the current? The current is 1 ampere and this is 10 to the power minus 5. So this is 3 into 10 to the power minus 5. It will be Newton per meter. Now, although not required, the book has an observation out here. If you see the definition of ampere, then the definition of ampere is a force which is 2 into 10 to the power minus 7. This is a much bigger force as compared to, so they say that hence it is important to eliminate the effect of Earth's magnetic field or any other stray field while standardizing the ampere. So when you try to measure an ampere, so in an ampere, how much force will the wires attract each other with? The wires will attract each other with 2 into 10 to the power minus 7. But already the Earth's magnetic field is behaving in much high value. So that force you cannot be able to even sense. Are you understanding? I say that you get fever, you have come from a different planet, and when your body temperature is something around 89 Fahrenheit, you get fever. You have come from a different planet. But you have come to Earth, and in Earth the ambient temperature itself is 94 Fahrenheit. So how do I test your fever? So I have to nullify the Earth's temperature, then only I can say that you have got fever. Are you getting that? So when you measure an ampere in lab, then you have to be very careful with that this part should be eliminated. Okay, this question has another part. It says when the current is from south to north. Look here. The next part is more interesting. These can come in 1-mark questions. The current is from south to north. Now in the next option, the current is in this direction, south to north. What is the angle between them? 0. So would it feel any force? No, the force felt will be 0. Okay? So these two we had to discuss, and today we are going to discuss about something called torque on a current carrying loop. Torque on a current carrying loop. And before going to torque on a current carrying loop, let us understand some basics of grade 10 and some definitions also, what is force and what is torque. So if you remember, a current carrying wire behaves like a magnet. All right, a current carrying wire behaves like a magnet. So if you take a current carrying wire and you put it in another magnetic field, like I'm just drawing the prelude to the derivation. Okay, so far I have a current carrying wire. So in all good sense, you will say that, sir, this is nothing but this is a magnet. Understood? This is a magnet. Now you take this magnet and you bring it in the vicinity of some external magnetic field. External magnetic field. This external magnetic field can be created by some permanent magnet, or it may be created by an electromagnet. That's not my lookout. But what I know is that I have a current carrying wire and I'm placing it in an external magnetic field. Magnet in a magnetic field. Definitely there will be an interaction. You remember in grade 10, we used to have that experiment where the wire is to get out from the mercury and again come back. Force on a current carrying conductor. So there will be a force on this current carrying conductor. This force can be attractive or can be repulsive depending upon what is the orientation of this magnetic field with this magnetic field. Is this concept understood or not? Right. Now, I just leave it for some time and I discuss with you force and torque. Torque is something which we study in rotational mechanics or rotational motion. Torque is supposed to create a twisting effect or a rotational effect. That means torque must have some force already with it. Otherwise, how will you rotate, right? So let's say this is a hexagonal nut, right? This is a hexagonal nut. And what you have done is you have put a spanner around it. You have put a spanner around it. And now what you're doing, you're trying to apply a force in this direction. You're trying to apply a force in this direction. And let's say this is an axis, right? And let's say I've got an arm out here. This arm is R. Will the nut rotate? Yes, the nut rotates. Combination of this and this actually gives you what is called a torque. I'm just trying to get your class 11 clear. This is a vector. We will take this also, moment arm also as a vector. Torque is given by the Greek letter tau, and it is said to be not F cross R, R cross F. R cross F. Right? Let us look which side is R beta. R is in this direction. And which side is F? F is in this direction. Do you agree or not? R cross F. Now just see. R, cross it to F. If you cross R with F, where is the thumb pointing? Inside. Now just think, if you put the spanner in this direction, don't you think the bolt will go inside? Yes, the torque goes inside. And if your F was upwards, R cross F, torque is outside. So if you move the spanner this side, the bolt ultimately comes out. Torque is a vector quantity. Number one, okay. Just like, so remember this definition. Another definition is just like force is mass times acceleration. Mass times acceleration. Torque in rotational kinematics, we say it is mass moment of inertia into angular acceleration alpha. Mass moment of inertia into angular acceleration alpha. This is ma, this is I alpha. Okay, before understanding torque a little bit more, now let's say what I do, I have got one wire, I have got one more wire, and I'm trying to make a loop of around it, whatever it is, and I try to generate a force on this wire in such a way that this wire wants to come out. Imagine, huh? And there is an axis out here. I've pivoted the wire. This wire wants to come out. At the same time, if you can generate a force which will actually push this arm inside, don't you think this should actually, like the IKEA door, it should just twist around? I'm saying on this, I would like to have a force on this side. On this, I would like to have an equal force on the other side. So this whole thing, like the door of IKEA, will just rotate. That we also call as, that is what is the job of torque. This is what we are going to study. You know that this wire will behave like a magnet. It will have an interaction as a force. I won't have a wire now. I will be having a loop, a current carrying loop, not a wire, okay? And the loop will be rectangular. The other thing you need to understand is a concept called couple. Couples are when two equal and opposite forces are separated by a distance. Say this is A, this is F, and this is F, equal and opposite, then they constitute what is called a couple, and the value of the couple is given by the force multiplied by the distance. So this will be, if you see from this side, it is half of A, F into half of A, F into half of A. So F into A is said to be the couple, right? If you see the couple from the torque's perspective, then it is like this. See, the more you can ask one question: why are the doorknobs at the edge of the door? Doorknobs are at the edge of the door because the door is pivoted there. I'm going to pull up with a force, and I should require minimum force. Who wants to work hard? So you are increasing the R. So here, when you actually, like steering wheel, the steering of a car, same force down, same force up. It's a couple. And where you have the maker's name, like a Toyota or a Honda, that is the pivot point. So the pivot point, if you see the torque out here, the torque will be given by force into A by 2 plus again this force into A by 2, because both of them are causing the same type of rotation. Force into A by 2, force into A by 2. So if you take force common, A by 2 plus A by 2, FA. So torque and couple's value comes same. Couple is typically when both are equal. This knowledge we will need as we are progressing now for our next set of derivation. Anything that you have not understood here. Okay. So write down the topic: torque on a current loop and the magnetic dipole. Torque on a current loop and the other topic along with this will be magnetic dipole. These two we're going to study. So let's make our diagram. So follow me as I make it. The first job is to make magnets. Okay. This is one magnet. At least play in rhythm. That's what I say. There should be some rhythm at least. This is the north pole of my magnet. South pole. Easy so far? Okay. After you have made the north pole and south pole, what we will make an axis for our loop. So that's my axis. And then I'll make my, but you can't say anything. That's it. So a bit of labeling. This is my magnet. So it's a magnet. This is actually a DC motor or a DC generator, though your book is not mentioning. But when we study electromagnetic induction, we will anyway study. This is my magnet. This is called the brush. Very common replaceable item in drill machines, mixer grinders. The brush wears out. This is called split ring. And in AC generator, you will have a slip ring. Brush and split rings together are called commutators. Anyway, we are not studying a motor, so don't bang your head. And let's say this is our loop AB, CD. Okay. And this is my rotation, and it is rotating with an angular velocity, say omega. This is my axis of rotation. Okay, I need to give it, this is a motor, so I need to give an external feed to it. So the feed is like this. Okay, the length of the magnet is taken to be B. This is A. So if the length of the magnet is B, means the length of, not magnet actually, the length of the loop is B. Okay, there, and this is your current. Then at any particular point, this is the magnetic field B. I'm just putting my arrow out here. Later I'll tell you what is this. Okay. Right. Fine, this much. This is B. Magnetic field always points from this. Okay. If you're done with your diagram, you can write down few things. So we have our, let's write down our considerations first. So we have a rectangular current. Write down rectangular considerations you can write, so that you did not write every time consider. So your consideration is a rectangular loop carrying current I, a rectangular loop carrying current I, that is point number 1. And in bracket you can write the current loop arrow tiny magnet. This is a tiny magnet. This is also a magnet now. The current loop is a, so right, current loop in bracket you just write it's a tiny magnet. Okay. And you can write what is your lookout or what is your quest. You can write your quest. Quest is what happens when a current carrying loop is introduced in a magnetic field. What happens when a current carrying loop is introduced in a magnetic field? What happens when a current carrying loop is introduced in a magnetic field? Carrying current I, this is the first one. And our next will be force on force. F. How do you find out F? F is always I into L cross B. Okay. So before we calculate the force, before I calculate the force, we'll write down another point. B is uniform. Write down B, magnetic field is uniform and is from North Pole to the South Pole. The magnetic field is uniform and is from North Pole to South Pole. That is, it is directed towards right. In such a case, the force experienced, force is equal to I into L vector cross B vector. Get your facts correct. What is I? I is the current on the conductor. L is the length of the current element. Okay. And B is the B will be what you call the magnetic field. This is our concept, right? Now we will write every arm of the rectangular, every arm of the rectangular loop is a current carrying conductor. Is a current carrying, don't you think? In every arm current is passing. As a children, before we actually start this also, let's go to grade 10 and see something. This is typically a DC motor. How does a DC motor rotate? Just look at this side of the arm, this arm. In this arm, let's apply Fleming's left hand rule like class 10. Magnetic F, B, I. B is pointing from left to right. I is coming from where, beta? Top to down. So the motion is in this side, force is in this side, means BC wants to come out. BC wants to come out. Agreed? And let's look at this one. At the same time, B is on this direction. F, B, I. B is on this direction. I is in the bottomwards direction. Then the F is on this direction. BC wants to come out of my screen, right? Just see the magic. What is happening at AD? At AD, again, B is in this direction. I is in the top direction. AD wants to go in. So it's like this, see? This fellow wants to come out, this fellow wants to go in. And that is how it rotates in DC motor. And if you actually change the polarity, it will rotate in the other way. Take any DC motor, give a connect supply to it, it will rotate. Change it, it will rotate in the other way. That means if it is rotating, please understand, in rotational mechanics, torque has to work. And torque is what? Force into moment arm. Force will be acting on these conductors, right? And just apply common sense, everything is easy. Force will be acting on this moment arm, which must be in opposite direction. I have to pull it this side, this one has to be pulled that side, then only it will rotate. And you will pivot it around here. So this much and this much will be equal arm lengths. And these conductors won't feel any force because the currents are along the direction of the magnetic field. Bas derivation ho gaya. Zero force out here. Here we will see equal forces. That's what we are going to find out. Guess the story easy now? So every arm of the rectangular loop is a current carrying conductor. So we will analyze each and every arm, but let me make this a little bit smaller now. Else I have to change the screen. Okay, every arm is a current carrying conductor. Now let's start our analysis. Let's start with the arm AD. Just look at AD as an arm. AD, what will you tell your force to be equal to? Force is equal to I, right? At AD, the theta will be equal to 90 degree. Just see, current is going up, current element is upwards, B is on this side, so theta will be 90 degree. That means sine 90 will be equal to how much? 1. So the force will be I, L cross B. So in our case, what is the L? In our case, the L is sine 90 is equal to 1. In our case, the L will be B. Have you understood this or not? B is the length of on this side, IBB. All right? Okay, fine. Now, then come to DC. At DC, theta makes 0 degree, right? Therefore, F will be equal to 0. Agreed? Right. Here we can mention one more thing. Force is inwards to the plane of paper. I'm writing paper. For me, screen. For you, it's paper. It's inwards. Have you understood? Okay. At DC is 0. So DC gone. After DC, what we are left with, beta? CB. At CB, theta is again equal to 90 degree. My force again becomes IBB. But here I would say force is outwards to plane of paper. Tick. And then I have finally what, beta? BA. At BA, my theta is equal to again 0 degree. Not exactly 0, but it is 180 degree. 180 degree. And so sine theta will become again 0. Therefore, there are only two components which are actually experiencing force. Right? Making this again go smaller. You have understood this part also. So I'm making this smaller now. And I'm putting it here. Clear? So can I now say arms AD and CB experience equal and opposite forces, which constitute a couple. Equal and opposite forces separated by a finite distance will always constitute a couple. Is that understood? Okay. Now, since the coil is pivoted around the axis of rotation, coil is, or not coil, I should use the word loop. Loop is pivoted around axis of rotation. It is pivoted around axis of rotation. Therefore, it experiences a torque. This will now experience a torque because see, I've pivoted your head and I'm pulling your ear by this side and by that side. Your head will rotate. So it's not torque. So the torque tau is given by the force, right, multiplied by A by 2, again F multiplied by A by 2. Why A by 2? But this distance is A. So arm becomes A by 2 around the pivot. Clear? So can we now write what is the torque's value? The torque, what is F? F value is IBB. So it becomes IABB. IABB. Bacha, have you understood or not? IABB. A by 2. Take F common. A. F is IBB. So IABB. And this is written as IAB. IAB. Where A is equal to area of the rectangular loop, which is equal to AB. This quantity IA, we'll study it a little bit more in detail, is actually known as M, which is magnetic dipole moment or magnetic moment. Magnetic dipole moment or magnetic moment. And I had left this yellow arrow, right? This yellow arrow is actually the magnetic moment, M. And now time has come for me to also give the position of the torque. So where do we create the torque? The torque will be exactly in this direction. Because how is my loop rotating? Look, my loop is rotating in this manner. The loop is rotating in this manner. So the torque is always seen from the axis. If you have slight bit of doubt, also go back to the spanner diagram. Your rotation, the torque is always coming out along the axis. This is the axis along which the nut is rotating. So the torque is to be seen as, the torque is coming out from here. So this is my tau. This is my tau. Okay. This M is known as the magnetic moment. Here, since magnetic moment is a vector quantity, I am putting an arrow out here and I am putting an arrow on A. I am putting an arrow on A. So you should ask, sir, what should be the direction? A means A is area vector. Go back to Gauss theorem. Any 2D surface, what is the area vector? The normal to the surface. The normal to the surface. That's why it is, this down means actually down on that side. Normal to the surface, that is called the middle. Now this is the generic case derivation, children. This is a very what you call generic case derivation. I'll tell you, have you understood this derivation? Okay, it comes IAB. Now why this is generic case? Because in this derivation, because whatever we have derived, we have very nicely assumed that the, what you call, the plane of the coil is actually lying, the plane of the coil is in such a manner that it is the area vector is perpendicular to the, what you call, magnetic field. In that condition, forces act only on this. There is no force on this. Have you understood what I am trying to say? I am trying to say that you have taken a very biased case where your loop is like this. Your loop could have been like this also. Then what happens? That is when the loop actually makes an angle theta, the loop or the area vector makes an angle theta with what? With your magnetic field. That is called the, that will be the general case derivation. This is a specific case derivation, and this derivation holds true, bacha, only when the area vector is perpendicular. So let's see our generic case derivation. So we have to make one more diagram, small one. Let's make it small. So we'll just make our coil now. Imagine this is your coil, and on these sides you have your magnets. Okay, this is your magnet on this side, and this is the magnet on the other side. Okay. And my current still continues to go in this direction. Have you understood now? It has just rotated. Now that rotation, how we will show? We will still show our magnetic field along the horizontal. So the magnetic field is along this direction. So this is the magnetic field. And then I have to bring out my, what you call, area vector or the M vector. And this is my area vector or M vector, whatever you say now. Okay. So, bacha, I'm writing something. I'm writing plane makes an angle with B. The plane makes an angle with B, or let's say we write it like this. Plane makes an angle between, one is magnetic field, which is B, and the other one is normal that is the area vector, not the plane. Okay, so the plane is now making an angle between the magnetic field and the area vector. The area vector's direction or the magnetic movement's direction is all same, so you can use either one. Is this understood? Acha. The only thing is that how do I make it smaller later? Otherwise, what is the area vector? The area vector is A, or it can be the M vector also. Now only the perpendicular components. What happens if you turn? Earlier you were taking how much beta? You were taking A by 2. Now it has turned. Whenever you turn, you have to take the perpendicular distance between the axis of rotation and the applied torque. See, in the first scenario it was very easy. This is axis of rotation and the torque and the force is on this side, so the perpendicular distance was very easy. Now you have shifted like this. Now your perpendicular distance is this, and this being theta, this being A, it will be A by 2 rather, it will be A by 2 sine theta. Are you able to understand what I'm saying? Earlier, this was my axis and this is the force. So your perpendicular distance was just A. Now you have shifted by theta. So the A has become hypotenuse and your perpendicular distance has shortened. That perpendicular distance is now A sine theta. So we can make the diagram also so that we make it smaller at one go. So if you have understood this diagram, this is fine. So I can make this smaller now. Okay, this is also something that you have understood. Now where does this M go from? Plane. Okay, so let's draw this diagram. If you have understood, it's fine. If you have not understood, then is the issue. So here I have got this much motion is B. This is along the direction of B, right? And your A has now, your original, whatever is the original one has got shifted like this. This is the original. So here I would write this as A by 2, and this is also A by 2, A by 2. Clear now? Okay, it has shifted, and then I have my vector M vector in this direction. So this angle is theta. This angle is theta. Our job is to actually now see the forces. The forces are now will be applicable. The forces will now be applicable like this. One force is in this direction, and the other force is in this direction. These are equal and opposite forces. And now this is the perpendicular distance. This will be 1 minute. This will be A by 2 sine theta. And this also will be A by 2 sine theta. So we write only, nothing changes, perpendicular distance between force and axis of rotation changes, nothing more than that. A becomes, A by 2 becomes A by 2 sine theta. So now your torque is equal to F into A by 2 sine theta plus A by 2 sine theta. F A sine theta, which can be now written as IAB sine theta. Did you understand? IAB sine theta, which can be written as IA sine theta into IABB. So IAB sine theta. IA, we are replacing it as MB sine theta. So in vector form, you can say torque is equal to M cross B. Torque is equal to M cross B. Now your job has been addressed. And how did you address it? You have addressed it like this. If theta is equal to 90 degree, torque is maximum. If theta is equal to 90 degree, torque will be maximum, and then it is given by M into B. And if theta is equal to 0 degree, your torque is equal to 0. That is, torque is minimum. Okay. Now see, when theta is 0, theta is equal to 90 degree, and when theta is equal to 0 degree. Now when theta is equal to 0 degree, what is theta 0? Try to understand. Theta 0 means when your A actually makes an angle 0 with this. When will A make an angle 0? Now it is like this, A is in this manner, right? If your coil is in this way, then A is making an angle 0 degree, means it makes an angle 0 degree. At that moment, that is at this 0 degree, you can write slight, I will not have space to write, so you write. When it is 0 degree, if you give a slight disturbance, remember torque in an electric field dipole in an electric field. So here also this is magnetic moment, means it's a magnetic dipole. See the beauty. When your A is making 0 degree, then your coil's position is not this, it's this. A is the perpendicular to the coil. A 0 degree, 0 with the magnetic field. At that moment, if you slightly displace it, system restores to original configuration, stable equilibrium. So you can write theta equal to 0, slight disturbance, torque brings it back. Slight disturbance, torque brings it back, and I call it stable equilibrium. Right? And when theta is equal to 180 degree or 0 degree, rather you can write theta equal to 180 degree, then slight disturbance will rotate the torque a lot. Yeah. So it is unstable equilibrium. वो रहेगा तो ऐसे, no doubt. So theta equal to 0. Theta equal to 0, slight disturbance, you come back. It will rotate like that rubber band. It will rotate. Yeah. So theta equal to, see, theta 0 also, the torque is 0. Theta 180 also torque is 0. But there's a difference. At 0, it will restore. At 180, it will turn heavily to restore to the original one. So at 0, it is stable equilibrium. At 180, it will be unstable equilibrium. At 0, stable equilibrium. At 180, it will be unstable equilibrium. Have you written that part? Okay. Now this is one coil. Suppose the coil has n turns. Write down. Suppose coil has n turns, capital N. If your coil has n turns, then your magnetic dipole moment, which was IA, will now become NIA, National Investigative Agency. What was IA becomes NIA. If loop, or say, if we say, if coil has n loops, if you have n loops, then your magnetic will say NIA. Then your torque becomes NIAB sine theta, means in magnitude. Nothing great I have written. See children, torque was IAB sine theta. IA is MB sine theta. It becomes NIAB sine theta. NIAB sine theta. Done. Now just write one, make one T column, and you write electric dipole, magnetic dipole. 3 lines and we are done. Electric dipole, magnetic dipole. One more class, children, which we will do galvanometer and this, and then we will be thorough with this chapter. Electric dipole. So write electric dipole and magnetic dipole. First you write the symbols. That is a P arrow and this is a M arrow. Remember that? P arrow, M arrow. What was the value of P? Tau cross E. P was equal to tau cross E. Electric dipole, magnetic dipole. Electric dipole was P vector. This is M vector. What was the value of P vector? Torque. No, in that case we used to say torque is equal to P cross E. P sine theta, you forgot. Torque is equal to P into E. Here torque will be M into B. Since they are so relational, electric dipole into electric field, magnetic dipole cross magnetic field. Clear? Acha, tell me that stable and unstable equilibrium, whenever you disturb the dipole, it will always align along E. That is what we studied in that chapter. So here you write aligns along E, here aligns along M. Aligns along M. Or aligns along B. Yeah, sorry. Aligns along B. Aligns along B. Now we are done. I'm just bringing the last line once again back. When it was 0 degree, it easily comes back to the direction. See, 0 degree means what? 0 degree means my A is actually like this, perpendicular to the plane, like this, 0 degree. So when you are shifting it from 0 degree, it wants to come back to B. But when you actually made it 180 degree, it will make a rigorous turn to come back to, at 180 also it is lying stable. But here if you do a little bit cherochari, na, it will pura twist and try to come back here. It goes back to the 0 degree. That's the same. That's why that's the last line. So therefore that unstable, at an unstable equilibrium also, see, if you ask, one more thing that I missed out, net force acting on the coils loop is 0. Net force is 0. But still movement will be there because couple, we wrote a line here, right? Constitute opposite forces constitute a couple. Here you can add a line. Net force on the system is 0. One force is this way, one force is that way. But still you have a couple being created. And once you have a couple being created, you cannot escape rotation. ठीक है ना? अब clear हुआ? Couple got created, that's why the rotation came once, and we get a value called m into b, but then we take a generic case and we bring the theta concept. How do you bring the theta? Thoda rotate kar do. So it's MAB sine theta. And that sine theta comes because earlier which was a by 2 has now become a by 2 sine theta. Okay? Fine. So we'll stop here then.